You are aboard a spacecraft, floating in the silent, inky abyss of interstellar space. The stars outside your window are ancient, their light having stretched across millions of years to reach your eyes. Every movement, every signal sent from your ship takes time to travel minutes, hours, even years to cross the cosmic void. But then, something impossible happens. A message appears on your screen, not carried by radio waves, not transmitted through light, but teleported. Its information woven into the very fabric of quantum reality. It did not travel the distance between its origin and your ship. It simply appeared. This is not a scene from science fiction. It is the strange and beautiful reality of quantum teleportation, a process where information, not matter, is transferred instantaneously, breaking the traditional rules of space and time. Unlike the teleporters of futuristic movies, quantum teleportation does not transport objects or people, but rather the very essence of their quantum state, the fundamental informational blueprint that defines them. But how is this possible? How can something leap across space without physically moving? To answer this, we must journey into the depths of quantum mechanics, into a world where particles can exist in multiple states at once, where entanglement links objects across vast cosmic distances, and where reality itself appears to be nothing more than a fragile, shimmering web of probabilities. This is the story of quantum teleportation, a phenomenon that challenges the very nature of existence, a discovery that could one day revolutionize communication, computing, and perhaps even our understanding of the universe itself. But before we can unlock the secrets of teleportation, we must first understand the bizarre, counterintuitive, and wonderfully mysterious quantum world that makes it all possible. There was a time, not so long ago, when physics was simple. The world was a clockwork universe, a grand deterministic machine where objects had precise locations, forces acted predictably, and the future was, in principle, calculable from the present. But at the dawn of the 20th century, this elegant, common-sense picture began to crumble. The quantum revolution arrived. A theory so strange, so counterintuitive, so profoundly weird, that even its own architects, like Albert Einstein, struggled to accept its full implications. At the heart of this revolution lies a disturbing and beautiful truth at the smallest scales. The universe does not behave in any definite way until we observe it. To understand why this is so profound, picture a simple marble rolling across a smooth table. In the classical world of our everyday experience, if you knew its exact position and its exact velocity, you could predict its entire future trajectory with perfect certainty. But in the quantum world, this certainty dissolves. The quantum marble, an electron, for example, does not have a single, definite position. It exists as a wave of probability, a diffuse cloud of potential locations, a superposition of all the places it could possibly be. It is not here or there. It is, in a very real sense, both here and there, and everywhere else in between, all at the same time. It is only when an observer looks, when a measurement is made, that this shimmering cloud of possibilities collapses, and the electron chooses a single, definite location. This is not just a mathematical trick or a philosophical abstraction. It is an experimental fact, one that has been confirmed time and time again. The famous double-slit experiment demonstrates this with an almost mystical clarity. When a beam of electrons is fired at a barrier with two narrow slits, and we do not try to determine which slit each electron passes through, an interference pattern appears on a detector screen behind the barrier. This pattern of alternating bright and dark bands is the classic signature of waves interfering with each other, like the ripples from two stones dropped in a pond. This happens even if the electrons are fired one at a time. Each individual electron seems to pass through both slits simultaneously, as a wave, and then interfere with itself. But the moment we place a detector at one of the slits to watch which path the electron takes, the wave-like behavior vanishes. The interference pattern disappears, and we see two simple bands on the screen, corresponding to the two slits. The electron now behaves like a well-behaved particle, choosing one path or the other. The very act of measurement, of gaining information, has changed the nature of reality itself. But if the principle of superposition is strange, the phenomenon of quantum entanglement is stranger still. Imagine two particles, born from the same quantum event, their fates forever intertwined. They fly apart, separated by miles, by light years, by the vast expanse of the cosmos. And yet, they remain connected by an invisible, instantaneous thread. This is quantum entanglement, a phenomenon so bizarre that Einstein famously called it spooky action at a distance. Entanglement means that two particles, no matter how far apart, are no longer independent entities, but are part of a single, unified quantum system. If you measure a property of one particle, say its spin, and find it to be clockwise, you instantly know, with absolute certainty, that its entangled partner, on the other side of the galaxy, will be found to be counterclockwise if you were to measure it. This instantaneous correlation seems to defy one of the most fundamental principles of physics, that no information can travel faster than the speed of light. Einstein was convinced that this spooky action was a sign that quantum mechanics was an incomplete theory. He believed that there must be some hidden variables, some unseen, predetermined properties of the particles that were secretly guiding their behavior. The particles, in his view, were like a pair of gloves, separated into two boxes. The moment you open one box and find a left-handed glove, you instantly know the other contains a right-handed one, not because of some spooky, faster-than-light communication, but because their states were determined from the very beginning. For decades, this was a philosophical debate. But in 1964, the physicist John Bell devised a brilliant mathematical theorem that transformed this debate into an experimental question. Bell's theorem established a set of inequalities that would have to be satisfied if any local hidden variable theory, like Einstein's, were correct. Quantum mechanics, on the other hand, predicted a clear violation of these inequalities. The stage was set for a definitive test of the nature of reality. And when the experiments were finally performed, with increasing precision over the decades, the results were undeniable. Bell's inequality was violated, time and time again. The universe is not locally real. The spooky action is real. The predictions of quantum mechanics, in all their strange and beautiful glory, were confirmed. This revelation was profound. It meant that at its core, the universe is not governed by the rigid, deterministic laws of classical physics, but by the strange, probabilistic, and deeply non-local rules of the quantum world. A particle's properties are not fixed until they are measured, and once measured, entangled particles seem to communicate their states instantaneously, in a way that defies our classical understanding of space itself. And it is this very spookiness, this non-local connection, that provides the key to one of the most revolutionary concepts in all of science, quantum teleportation. Teleportation is not about physically moving an object from one place to another. It is about transferring its quantum state, the very essence of its identity, the complete informational blueprint that describes its properties, without sending the object itself. And to do this, we must use the strange and powerful magic of entanglement. The process of quantum teleportation is a delicate and beautiful dance of quantum principles. It is a process that seems, at first glance, to be a paradox, a violation of the very laws it relies on. But upon closer inspection, it is a stunning testament to the strange and beautiful logic of the quantum world. The process begins with an essential ingredient, a pair of entangled particles. Let's call them particle A and particle B. These two particles are created in such a way that their quantum states are perfectly correlated. One of these particles, A, is kept at the sender's location. The other, B, is sent to the receiver, who may be light years away. Now, a third particle, let's call it particle C, is introduced. This is the particle whose quantum state we want to teleport. Particle C is brought into contact with the sender's entangled particle, A, and a special joint measurement is performed on them. This measurement, known as a Bell state measurement, does something remarkable. It forces the combined system of A and C into one of four possible entangled states, and in doing so, it has a profound and seemingly destructive consequence. The original quantum state of particle C is completely erased. It no longer exists at the sender's location, but the information has not been lost. It has, in a sense, been imprinted onto the distant, entangled particle, B, at this moment, the receiver's particle, B, has absorbed the quantum information from particle C, but it remains in a scrambled, incomplete form to complete the teleportation. A final crucial step is required. The sender must communicate the result of their Bell state measurement, a simple 2-bit piece of classical information, to the receiver. This message must travel through normal space, at or below the speed of light. Once the receiver has this classical information, they know which of the four possible outcomes occurred at the sender's end, and they can perform a specific, simple transformation on their particle, B. And with that final touch, particle B becomes a perfect, identical replica of the original particle C, possessing the exact same quantum state that was destroyed at the sender's end a moment before. The teleportation is complete. The information has been transferred. But what makes this process so strange and so profound is that nothing physical has traveled between the two locations. The quantum state did not move through the intervening space. The particle at the receiver's end was never in physical contact with the original. And yet, somehow, the exact and incredibly fragile quantum information has been perfectly reconstructed, as if by magic. This raises a deep and fundamental question. Where was the information during its journey? One interpretation is that quantum states are not localized entities at all. They are non-local patterns of probability spread out across space-time. In this view, teleportation is not a process of movement in the classical sense, but is a rearrangement of this non-local information, a shifting of the quantum state from one physical carrier to another, a process that is not constrained by the normal rules of spatial separation. Another related perspective comes from the framework of quantum field theory, which, as we have seen, suggests that particles are just excitations of an underlying universal quantum field. In this view, teleportation is not about moving a thing from point A to point B, but is an operation on the field itself, a process that causes the quantum state to demanifest at one location and re-manifest at another. Regardless of the interpretation, one thing is clear: quantum teleportation, while seemingly instantaneous at the quantum level, does not allow for faster-than-light communication. The need to transmit the classical information about the measurement outcome ensures that the overall process is always limited by the speed of light, preserving the sacred principle of causality and keeping Einstein's theory of relativity intact. But this does not make the process any less remarkable. Quantum teleportation is a direct and powerful demonstration of the deeply non-local nature of reality. It is a process that is only possible because the universe At its core is not a collection of separate, independent objects, but a single, holistic, and entangled system. And it is a process that has already been achieved in laboratories around the world. Scientists have successfully teleported the quantum states of photons, of atoms, and even of small molecules over increasingly large distances. The future of this technology is one of incredible promise. It is the key to building a secure, unhackable quantum internet. It is the foundation for creating large-scale, distributed quantum computers. And it is a powerful tool for probing the very nature of reality itself. But as we stand on the threshold of this new quantum informational age, we are also forced to confront some of the deepest and most unsettling questions about our own existence. If the very essence of a particle, its informational soul, can be erased and reborn elsewhere, what does that mean for our own human sense of identity, of continuity, of the self? The strange magic of quantum teleportation is not just a technological trick. It is a profound and deeply philosophical challenge to our most cherished assumptions about what it means to be real. The question of whether quantum teleportation could one day be applied to a human being is one that pushes the boundaries of science, of ethics, and of philosophy. It is a question that forces us to confront the very nature of our own identity, of our consciousness, of the self. At first glance, the idea seems like the ultimate science fiction dream: to step into a machine, to be dematerialized, and to be instantaneously reconstructed on a distant planet, a perfect copy of your former self. But the quantum reality of teleportation is far stranger and far more unsettling than this simple picture would suggest. The first and most crucial thing to understand is that quantum teleportation does not transport matter. It transports information. To teleport a human being, you would not be sending their atoms across space. You would be scanning the complete quantum state of every single particle in their body, an almost infinitely complex task, destroying the original in the process, and then using that information to reconstruct a new body, atom by atom, at the destination. This is not a process of movement. It is a process of destruction and recreation. And this is where the profound and deeply troubling philosophical problems begin. The no-cloning theorem of quantum mechanics, as we have seen, states that it is impossible to create a perfect, identical copy of an unknown quantum state. This means that if you were to be teleported, there could be no backup copy of you. The original you, the one who stepped into the machine, would have to be destroyed for the new you to be created. The process is one of replacement, not duplication. So, is the person who emerges at the other end still you? From a purely physicalist or functionalist perspective, the answer might be yes. If consciousness is nothing more than a complex pattern of information, a specific arrangement of neural connections and quantum states in the brain, and if that pattern is perfectly replicated, then the subjective experience of consciousness should, in theory, continue seamlessly. The new you would have all the same memories, the same thoughts, the same feelings, the same sense of self. For them, it would be as if they had simply closed their eyes in one place and opened them in another. But this is where the thought experiment of a malfunctioning teleporter becomes so powerful and so disturbing. Imagine the machine scans you, transmits your information, and reconstructs you at the destination. But due to a glitch, it fails to destroy the original you. Now there are two of you. Both are physically identical. Both have the same memories. Up until the moment of teleportation, both believe, with absolute conviction, that they are the real you. Which one is right? Who has the claim to your life, to your relationships, to your past? This scenario highlights a deep problem with a purely functionalist view of identity. It suggests that there may be something more to the self than just a pattern of information. There is also the issue of continuity of consciousness. We have a powerful, intuitive sense that our self is a continuous, unbroken stream of experience, a single thread that runs from our birth to our death. The process of teleportation, of destruction and recreation, seems to violently sever this thread. Would the original you experience a moment of annihilation, a final terrifying end? And would the new you just be a perfect, but ultimately soulless copy, a philosophical zombie that looks and acts just like you, but has no genuine inner subjective experience? Some theories of consciousness, like the orchestrated objective reduction model, suggest that this might indeed be the case. If consciousness is a real physical, a quantum process that is tied to the specific physical structure of the brain, then it may not be something that can be simply copied and pasted into a new physical substrate. The delicate quantum coherence that gives rise to our subjective experience might be a unique and non-transferable property of our original biological brain. In this view, the teleported you would be a perfect physical replica, but it would be an empty shell, a being without a soul. But even if we set aside these more exotic theories of consciousness, the very nature of time and perception in the teleportation process raises a host of unsettling questions. If the reconstruction process at the destination is delayed by 10 minutes, what does the teleported person experience? Do they exist in a state of nothingness for those 10 minutes? Or do they experience an instantaneous jump forward in time, a gap in their subjective experience that they can never account for? And what if the reconstruction process fails entirely? If the original you is destroyed, but the new you is never created? Have you died, or from your own subjective perspective, have you simply ceased to exist at a particular moment, with no experience of death at all? These are not just scientific questions. They are deep, existential riddles that touch on the very meaning of what it means to be alive, to be a person, to have an identity. If teleportation were ever to become a reality for human beings, it would force a profound, and perhaps painful, reevaluation of our most deeply held beliefs about the self. It could lead to a new and more fluid understanding of identity, where the self is not a fixed, singular entity, but a pattern that can be moved, that can be stored, that can perhaps even be branched. It could open up the possibility of a new kind of immortality, where our minds are not tied to a single, fragile, biological body, but can be backed up, transferred, and restored. But it would also open up a Pandora's box of new and deeply challenging ethical and social dilemmas. The question of teleportation is not just about whether we can do it. It is about whether we should. And it is a question that forces us to confront the possibility that our cherished and seemingly solid sense of a continuous, singular self is just a fragile and beautiful illusion. An illusion that the strange and powerful magic of quantum teleportation threatens to expose. The paradox of a malfunctioning teleporter, the scenario where an original and a copy of a person coexist, leads us down a rabbit hole of even deeper and more mind-bending quantum possibilities. It forces us to confront the idea of quantum immortality, a strange and unsettling consequence of the many worlds interpretation of quantum mechanics. In the many worlds view, as we have seen, every quantum event causes the universe to split into multiple parallel branches, with each branch corresponding to a different possible outcome. If a teleportation machine has even a minuscule 1 in a trillion chance of malfunctioning and failing to destroy the original, then in the vast branching tree of the multiverse, there must be a branch where this failure occurs. From an external, the third-person perspective, the vast majority of teleportation events are successful. The original is destroyed, the copy is created, and the process works as intended. But what about from the first-person, subjective perspective of the person stepping into the machine? This is where the idea of quantum immortality comes in. The theory suggests that your consciousness, your subjective stream of experience, will always, and only, follow the branches of the multiverse where you survive. You can never, by definition, experience a reality in which you have ceased to exist. So, if there is a branch of reality where the teleporter malfunctions and the original you is not destroyed, then your consciousness must, according to this theory, follow that branch. From your perspective, you would step into the teleporter. The machine would whir and hum, and then nothing would happen. You would emerge, unscathed, to be told by a surprised scientist that the teleportation had failed, but that a perfect copy of you had, in fact, been created at the destination. For the rest of the world, there are now two of you. But for you, the original, your stream of consciousness has remained unbroken. This has a truly bizarre and deeply unsettling implication. It suggests that from your own subjective point of view, you can never die in a teleportation event. You will only ever experience the realities in which you survive. It is a form of personal probabilistic immortality. This idea can be extended beyond teleportation to any life-threatening event. If you are in a car crash and there is even a tiny, non-zero quantum probability that you will swerve at just the right moment to survive, then, in the many worlds picture, there is a branch of reality where you do, and your consciousness will follow that branch. Everyone in the other branches will mourn your tragic death, but you will experience a miraculous and seemingly impossible escape. Over the course of a long life, a person who believes in quantum immortality would find themselves living a charmed and increasingly improbable existence, surviving against all odds, a living testament to the fact that their consciousness is always and only on the winning side of the cosmic quantum coin toss. This is a strange and deeply counterintuitive idea, and it is one that is, of course, highly speculative and untestable. But it is a logical consequence of taking the many worlds interpretation of quantum mechanics seriously. And it completely reframes our understanding of what teleportation would mean for the self. It would not be a simple process of movement from A to B. It would be a process of branching, of creating new versions of reality. Every time you step into a teleporter, you are not just traveling. You are playing a game of quantum Russian roulette, a game in which, from your own perspective, you can never lose. But what does this do to our sense of identity? If there are an infinite number of yous branching off with every quantum event, which one is the real you? The many worlds interpretation suggests that they are all equally real. Identity is not a single, continuous thread, but a vast and ever-growing, branching tree. This is a vision of the self that is far more fluid, more multiplicitous, and more deeply connected to the probabilistic nature of the cosmos than our classical intuition would ever allow. The implications for human society would be profound. How would our legal systems deal with the existence of multiple identical copies of a person who would be responsible for the actions of a branched self? How would our concepts of love, of family, of inheritance be transformed in a world where identity is no longer singular? The psychological impact would be equally staggering. Would the knowledge that you are constantly branching into other realities lead to a sense of existential liberation, or to a profound and dizzying sense of personal dissolution? Would people embrace the fluid, branching nature of the self, or would they cling, with even greater desperation, to the illusion of a single, stable identity? And what about the ethics of teleportation itself? If every use of a teleporter creates a new branch of reality, are we, in a sense, polluting the multiverse with an endless proliferation of copies? These are questions that are on the very frontier of our scientific, philosophical, and ethical thinking. They are questions that are born from the strange and beautiful marriage of our most advanced physical theories with our deepest and most enduring questions about the nature of the self. Quantum teleportation, in this light, is not just a technological dream. It is a philosophical mirror, a tool that reflects back to us the deep and often unsettling quantum nature of our own human existence. It forces us to confront the possibility that we are not the solid, singular, and continuous beings we believe ourselves to be, but are something far stranger, more fluid, and more wonderfully mysterious, a branching, probabilistic, and perhaps even immortal wave of consciousness, forever surfing the crest of an infinite quantum sea. The strange and powerful phenomenon of quantum teleportation does not just challenge our understanding of space, it also, and perhaps even more profoundly, challenges our understanding of time, our classical. Everyday intuition tells us that time is a one-way street, a river that flows inexorably from a fixed past, through a fleeting present, to an open future. But the quantum world, with its non-local connections and its probabilistic nature, seems to hint at a more complex and more mysterious temporal reality. And quantum teleportation may be the key that allows us to unlock its secrets. At its core, teleportation is about the transfer of quantum information, and this information, as encoded in the state of an entangled system, seems to exist outside the normal constraints of space. The connection between two entangled particles is instantaneous, regardless of the distance between them. But if this connection can transcend space, could it also transcend time? Could quantum teleportation be used not just to send a message across the galaxy, but also to send a message back to yesterday? This is a radical and deeply challenging idea, but it is one that is not entirely ruled out by the laws of quantum mechanics. The equations of quantum mechanics are, for the most part, time-symmetric. They work just as well for a process running backwards in time as they do for one running forwards. This has led some physicists to speculate that the non-local connection of entanglement may not just be a spatial one, but a temporal one as well. Two particles could be entangled in time, with a measurement on a particle in the future having an instantaneous effect on the state of a particle in the past. The famous delayed choice quantum eraser experiment is a stunning and deeply perplexing demonstration of this kind of apparent backward-in-time influence. In this experiment, the choice of whether or not to measure the which path information of a photon seems to retroactively determine whether that photon behaved as a particle or a wave in the past. It is as if a decision made in the present can reach back and change the nature of a past event. This does not mean that we can send a controllable message back in time to change history. But it does suggest that the relationship between the past, the present, and the future at the quantum level is far more subtle, more holistic, and more mysterious than our classical intuition would ever allow. Could quantum teleportation be used to harness this strange temporal non-locality? Imagine a scenario involving entanglement swapping. You can take two independent pairs of entangled particles, and by performing a specific joint measurement on one particle from each pair, you can swap the entanglement so that the two previously unconnected particles from the different pairs become entangled with each other. Now, what if one of these entangled pairs was created in the distant past, and the other is created in the present? By performing an entanglement swap, you could, in theory, create an entangled link between a particle that exists now and a particle that existed then. You would have created a quantum channel that connects two different points in time. Could this channel be used to teleport a quantum state from the present to the past? This is a highly speculative and technically challenging idea, but it is one that is being seriously explored by some theoretical physicists. And it opens up the breathtaking possibility of a new kind of time travel. A time travel not of physical objects, but of pure quantum information. This would be a form of time travel that could potentially bypass some of the famous paradoxes of classical physical time travel. You could not go back and kill your own grandfather because you cannot teleport a macroscopic object. But you might be able to send a single qubit of information back, a quantum message that could perhaps influence the probabilities of past events. But even if such a process were possible, the universe may have its own built-in chronology protection mechanisms. The self-consistency principle, proposed by physicists like Igor Novikov, suggests that even if time travel is possible, the laws of physics will conspire to prevent any paradoxes from occurring. Any action you take in the past will be, in a sense, self-consistent. If you were to send a message back in time to warn yourself not to step into the street and get hit by a bus, something would have to happen to prevent you from receiving or acting on that message. The bus would still hit you. The outcome would be consistent with the fact that you were there, in the future, to send the message in the first place. The many worlds interpretation of quantum mechanics offers another, and perhaps more elegant, solution. If you were to send a quantum state back in time, you would not be sending it back into the past of your own universe. You would be sending it to a different parallel branch of the multiverse. You could change the past in that universe, but it would have no effect on your own. Personal history. The timeline would remain consistent because you have simply created a new and different one. The deep and mysterious connection between quantum teleportation and the nature of time is a frontier of scientific inquiry that is still in its infancy. But it is a frontier that is full of profound and potentially revolutionary possibilities. It is a frontier where the strange, non-local magic of the quantum world seems to touch upon the deepest and most enduring mysteries of our own temporal existence. Is it possible that our own consciousness, with its strange and often non-linear relationship with time, is a macroscopic manifestation of these deep quantum temporal effects? Could our flashes of intuition, our moments of déjà vu, our precognitive dreams be the result of our brains as quantum systems, tapping into the subtle temporal entanglements of the universe? These are speculative questions, to be sure, but they are questions that are no longer just the domain of the mystics and the philosophers. They are questions that are beginning to be asked in a new and more rigorous way by the physicists who are probing the very heart of quantum reality. Quantum teleportation has shown us that our classical, intuitive understanding of space is a profound illusion, and it may be that its greatest and most unsettling. Revelation is still to come that our classical, intuitive understanding of time is an illusion as well. The strange, non-local, and instantaneous nature of quantum teleportation does more than just challenge our classical notions of space and time. It forces us to confront an even more radical and more profound possibility that the universe itself is a vast, interconnected teleportation network. In this vision, space is not a fundamental, empty void that separates objects, but is an emergent illusion, a macroscopic manifestation of a deeper and more fundamental level of quantum informational connectivity. The universe is not a collection of separate things. It is a single, holistic, and entangled system, where every part is in instantaneous communication with every other part. This is an idea that has its roots in the holographic principle and the Eier-Upper conjecture, which, as we have seen, suggests that the geometry of space-time is a holographic projection of the underlying quantum entanglement between its constituent parts. In this view, the universe is not in space. Space is in the universe. The seemingly vast distances between the galaxies are not a measure of a fundamental separation, but are a reflection of the weakness of the entanglement between those distant regions. Two particles that are right next to each other are strongly entangled. Two galaxies that are billions of light-years apart are very weakly entangled, but the connection is still there. If this is the case, then quantum teleportation is not a strange, anomalous process that violates the normal rules of space. It is a direct and powerful manifestation of the true, underlying, non-local nature of reality. It is not about sending information across space. It is about accessing the hidden, informational pathways that are the very fabric of space itself. This would mean that our current and technologically challenging methods of teleportation, which rely on the creation and distribution of entangled particle pairs, are just a clumsy and very inefficient way of tapping into a universal process that is happening naturally and continuously at every point in the cosmos. This vision of a teleportation universe has the potential to shed new light on some of the deepest and most perplexing mysteries of modern astrophysics. The phenomenon of fast radio bursts, for example, is a major puzzle. These are incredibly bright and incredibly short, bursts of radio waves that seem to be coming from distant galaxies. Some of these bursts repeat with a strange and often eerie periodicity. The source of these bursts is completely unknown, and they release an immense amount of energy in a fraction of a second. Could it be that these are not astrophysical explosions in the classical sense, but are a form of natural, large-scale quantum teleportation event? A momentary, coherent collapse of the wave function of a vast number of entangled particles. A glitch in the cosmic teleportation network. The existence of ultra-high energy cosmic rays is another long-standing puzzle. These are single, subatomic particles that arrive at the Earth with an energy that is millions of times higher than anything we can produce in our most powerful particle accelerators. The problem is that these particles should not be able to travel across vast intergalactic distances without losing their energy through interactions with the cosmic microwave background radiation. And yet, we see them. Could it be that these particles are not traveling to us in the classical sense at all? Could they be teleporting from their distant sources, arriving at the Earth with their energy intact, having bypassed the long and energy-sapping journey through intergalactic space? These are, of course, highly speculative ideas, but they are a testament to the fact that the universe is full of phenomena that do not seem to fit our simple, classical, and local understanding of reality. And the idea of a universal teleportation network provides a new and potentially powerful framework for thinking about these mysteries. But the implications of a teleportation universe extend far beyond the realm of astrophysics. It has profound implications for the future of our own technological civilization. If the universe is a natural teleportation network, then the ultimate form of travel and communication may not be about building faster spacecraft or more powerful transmitters. It may be about learning to hack the code of the cosmos, to tap into the underlying quantum informational network that connects all of reality. A sufficiently advanced civilization might not need to travel through space at all. They might be able to simply relocate themselves, to teleport their matter, their energy, and perhaps even their consciousness from one point in the universe to another by manipulating the deep entanglement structure of space-time itself. This could be the ultimate explanation for the Fermi paradox, The puzzle of why we have not yet seen any evidence of other, advanced, extraterrestrial civilizations. Perhaps they are not traveling between the stars in physical spaceships. Perhaps they have graduated to a higher, more efficient, and more subtle form of existence. A form that is based on the direct manipulation of the quantum informational fabric of the cosmos. They are not out there to be seen. They are everywhere, woven into the very structure of reality itself. This vision of a teleportation universe is a vision that is both breathtakingly beautiful and deeply humbling. It is a vision of a cosmos that is far more interconnected, more intelligent, and more mysterious than we can yet fully comprehend. And it is a vision that places information and its strange, non-local quantum properties at the very heart of reality. The universe is not a dead, mechanical thing. It is a living, breathing, and constantly communicating quantum web. And we, as conscious, questioning beings, are not just passive observers of this web. We are an integral part of it. Our own consciousness, with its strange and often non-local properties of intuition, of empathy, of creativity, may be a macroscopic manifestation of the same deep quantum connectivity that allows for the spooky action of entanglement and the magical process of teleportation. We are not just in the network, we are the network. The quest to understand quantum teleportation is not just a quest to build a new kind of technology. It is a quest to understand the very nature of our own reality. And it is a quest that is leading us to a new and profoundly different picture of the cosmos. A picture where space is an illusion, where time is a mystery, and where the universe itself is a single, vast and beautifully interconnected quantum thought. For decades, the strange and beautiful phenomenon of quantum teleportation was a curiosity confined to the esoteric world of theoretical physics and the carefully controlled environment of the laboratory. It was a stunning demonstration of the bizarre, non-local nature of the quantum world. But its practical applications seemed to be a distant, and perhaps even unattainable, dream. But that is no longer the case. We are now living at the dawn of a new, quantum technological revolution. A revolution that is poised to take the strange magic of teleportation out of the lab and into the real world. A revolution that has the potential to reshape our society, our economy, and our very understanding of information itself. The most immediate and most transformative application of this new technology is in the field of quantum communication. In our current classical world, all our communication, from a simple phone call to a classified government document, is fundamentally insecure. It relies on the principles of classical cryptography, which are based on the computational difficulty of solving certain mathematical problems. But these codes can, in principle, always be broken by a sufficiently powerful computer. And with the advent of quantum computers, which have the potential to solve these problems exponentially faster than any classical machine, the entire foundation of our modern digital security is under threat. Quantum teleportation and the principles of quantum mechanics upon which it is based offer a new and fundamentally different kind of security. It is a security that is not based on computational difficulty, but on the very laws of physics themselves. The no-cloning theorem and the observer effect guarantee that any attempt to eavesdrop on a quantum communication channel will inevitably disturb the system and leave a detectable trace. This allows for the creation of unhackable communication systems, systems where the security is guaranteed by the fundamental nature of reality itself. The technology of quantum key distribution is the first practical application of these principles, and China, with its ambitious and highly successful Mickey's satellite program, has already demonstrated the feasibility of creating a global quantum-secure communication network. In 2017, Chinese scientists successfully teleported the quantum state of a photon from a ground station in Tibet to the Mixius satellite in orbit, a distance of over 1,400 kilometers. It was a stunning and world record-breaking achievement, a clear demonstration that quantum teleportation is no longer just a laboratory experiment, but is a viable technology for global, secure communication. The race to build a quantum internet is now on, with governments and tech giants around the world investing billions of dollars in the research and development of the necessary technologies. A mature quantum internet would not just be a more secure version of our current internet. It would be a new kind of network, a network that can transmit not just classical bits, but fragile, quantum qubits of information. This would allow for the connection of quantum computers around the world, creating a global, distributed quantum supercomputer. The impact of such a technology on science, on medicine, on finance, on artificial intelligence would be almost impossible to overstate. This brings us to the second great technological revolution that is being powered by the principles of quantum information, quantum computing. As we have seen, a quantum computer is not just a faster version of a classical computer. It is a fundamentally different kind of machine. A machine that operates on the strange and powerful logic of the quantum world. And quantum teleportation is a crucial and enabling technology for building a large-scale, fault-tolerant quantum computer. One of the greatest challenges in quantum computing is the problem of decoherence, the tendency of the fragile quantum states of the qubits to be destroyed by their interaction with the environment. To build a powerful quantum computer, you need to be able to connect a large number of qubits together. But the more qubits you have, the more susceptible the system is to decoherence. Quantum teleportation provides a potential solution to this problem. It allows for the transfer of quantum information between different parts of a quantum computer, or even between different quantum computers in a network, without the need for a direct physical connection. You can teleport a qubit from a noisy computational part of the processor to a quiet, protected quantum memory, preserving its fragile state. You can use teleportation to create the long-range, entangled connections that are necessary for the implementation of powerful quantum error correction codes. The algorithms that will be needed to protect a quantum computation from the destructive effects of decoherence. In this sense, quantum teleportation is not just a communication protocol. It is an essential architectural component of any future large-scale quantum computer. It is the quantum wire that will allow us to build machines of unprecedented computational power. The societal and economic implications of this are staggering. A mature quantum computer could revolutionize the process of drug discovery and material science by allowing us to simulate the behavior of molecules with perfect quantum accuracy. It could transform the field of finance by solving complex optimization problems that are currently intractable. And it could supercharge the development of artificial intelligence by providing a new and far more powerful computational substrate for machine learning algorithms. But with this great promise also comes great peril. A powerful quantum computer would also be able to break most of the classical cryptographic codes that protect our current global financial and communication systems, creating a new and potentially devastating security threat. The race to develop quantum-resistant classical cryptography and to build a truly secure quantum internet is one of the most urgent and most important technological challenges of our time. The technological revolution of quantum teleportation is not just about building better computers and more secure communication networks. It is a revolution that is forcing us to confront some of the deepest and most unsettling questions about the nature of our own human existence. The possibility, however remote, of one day being able to teleport the complete quantum state of a complex biological system, or even of a human being, is a prospect that is full of both breathtaking promise and profound existential dread. As we have seen, This is not the beaming of science fiction. It is a process of destruction and recreation. And it raises a host of deep, philosophical questions about the nature of identity, of consciousness, of the self. Is the person who emerges at the destination still you? Or are you just a perfect, but ultimately soulless copy? These are questions that may not have a simple scientific answer. They are questions that touch on the very meaning of what it means to be human. But even if we never teleport a human being, the very fact that the laws of physics allow for the perfect, non-local transfer of information is a profound and deeply transformative revelation. It tells us that our classical, intuitive understanding of the world, a world of separate, localized objects, is a profound illusion. The true reality is a much more interconnected, more holistic, and more mysterious quantum web. And as we learn to harness the strange and beautiful power of quantum teleportation, we are not just building a new set of technologies. We are learning to see the world and ourselves in a new and more profound light. We are moving from a worldview that is based on separation to one that is based on connection. We are moving from a reality of things to a reality of information. And we are moving from being passive observers of the cosmos to becoming its active and conscious co-creators. The journey into the age of quantum teleportation is a journey that is full of both immense promise and profound ethical challenges. It is a journey that will require not just scientific and technological ingenuity, but also a new level of philosophical wisdom, of social foresight, of human maturity. And it is a journey that is just beginning. The strange, spooky, and beautiful magic of the quantum world is no longer confined to the laboratory. It is coming into our world, and it is a world that will never be the same again. The ultimate question that the phenomenon of quantum teleportation forces us to confront is not about technology, not about communication, not even about the nature of space and time. It is a question about the very nature of reality itself. If information can be transferred from one location to another, instantaneously and without traversing the intervening space, then what does this tell us about the fundamental structure of the universe we inhabit? It suggests a reality that is far stranger, more interconnected, and more profoundly mysterious than our classical. Common sense intuition would ever lead us to believe. For centuries, our scientific worldview has been built on the foundation of locality, the idea that an object can only be influenced by its immediate surroundings. But quantum entanglement, the engine behind teleportation, shatters this foundation. It reveals a universe that is fundamentally non-local, a universe where the concept of distance itself may be an illusion. The two entangled particles, separated by light years, are not two separate things. They are two aspects of a single, indivisible, quantum whole. To touch one is to touch the other. This is a vision of the cosmos that is not a collection of objects in space, but is a single, vast, and interconnected quantum system. A system where space is not a fundamental, pre-existing container, but is an emergent property of the underlying quantum informational relationships between its constituent parts. This is the essence of the holographic principle. The idea that our three-dimensional reality is a projection of information encoded on a lower dimensional surface. In this view, quantum teleportation is not a process of information traveling at all. It is a direct manipulation of this underlying holographic code, a rearrangement of the informational bits and qubits that constitute the very fabric of reality itself. This is a profound and deeply transformative shift in our understanding of the cosmos. It suggests that the true fundamental reality is not the world of matter, of energy, of space and time that we perceive with our senses. The true reality is a world of pure quantum information, a world of abstract, mathematical relationships, a world of non-local, entangled connections, and the physical universe we experience is just a shadow, a projection, a fleeting and partial manifestation of this deeper and more fundamental informational reality. This informational view of the universe has the potential to unify some of the deepest and most disparate concepts in modern physics. The mysteries of dark matter and dark energy, the puzzle of quantum gravity, the nature of time's arrow. All of these may find their ultimate explanation in a deeper and more complete understanding of the quantum informational structure of the cosmos. The universe, in this vision, is not just a physical system, it is a computational one. And we, as conscious, questioning beings, are not just passive observers of this cosmic computation. We are an integral part of it. Our own consciousness, with its strange and often non-local properties of intuition, of empathy, of creativity, may be a macroscopic manifestation of the same deep quantum connectivity that allows for the spooky action of entanglement and the magical process of teleportation. We are not just in the universe is in us. And the quest to understand the one is inseparable from the quest to understand the other. The journey into the strange and beautiful world of quantum teleportation is a journey that has taken us from the laboratory bench to the very edge of reality itself. It is a journey that has challenged our most deeply held beliefs about space, about time, about identity, about existence. And it is a journey that has left us with more questions than answers. Is our universe just one of a vast and perhaps infinite number of other parallel realities? Is the flow of time an illusion? Is consciousness a fundamental and creative aspect of the cosmos? These are questions that may not have a simple or a final answer, but they are the questions that drive us forward. The questions that fuel our relentless and beautiful human quest for knowledge and for meaning. Quantum teleportation is more than just a scientific breakthrough, it is a philosophical revelation. It is a mirror that reflects back to us the deep, strange, and wonderful mystery of our own quantum existence. And it is an invitation, a call to adventure, a challenge to see the world and ourselves, not as a collection of separate, solid, and certain things, but as a single, vast, and beautifully interconnected quantum song. A song whose notes are still being written. A song whose final and ultimate meaning we are all, together, creating. Quantum mechanics offers a world that feels vastly different from what we encounter in our everyday lives. A world that challenges our most fundamental sense of order and predictability. Unlike the classical physics of Newton, which thrives on definitive outcomes, on measurable certainties, on a universe that operates like a grand, predictable clockwork machine. The quantum realm is a world of probabilities, of uncertainties, and of strange, counterintuitive principles. At its very core lies the uncertainty principle, a profound and beautiful declaration that it is impossible to simultaneously determine the exact position and the exact momentum of any particle. This is not a limitation of our technology, not a fault in our methods of observation. It is an inherent, built-in property of nature itself. The principle, first introduced by the German physicist Werner Heisenberg, states that the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It is a cosmic trade-off, a fundamental limit to our knowledge. This peculiar and beautiful truth reshapes our entire understanding of how particles move and interact. It forces us to abandon the dream of a perfectly predictable, deterministic universe, and to accept a reality where chance and randomness play an intrinsic, and perhaps even creative, role. The implications of this principle extend far beyond the simple act of measurement. They give rise to some of the most bizarre and wonderful concepts in all of science, including the idea of zero-point energy. This is a minimal, irreducible energy that remains in any physical system, even when it has been cooled to absolute zero, even when all its observable thermal energy seems to have been removed. In the classical world, cooling a system to absolute zero should bring all its constituent particles to a complete, perfect halt. But quantum mechanics forbids this. The energy that is tied to the inherent quantum motion of a particle can never be entirely eliminated. Even in their quietest, lowest energy states, particles are in a constant, jittery, and restless motion. This ceaseless behavior originates directly from the fundamental uncertainty in knowing both a particle's position and its momentum at the same time. These microscopic movements, often described as quantum jitters, are a reflection of the deep, ever-present, and dynamic activity that lies at the very heart of the quantum world. The energy that is associated with these ceaseless quantum fluctuations is not just a theoretical curiosity. It is a real physical phenomenon with measurable effects. It influences the behavior of systems in profound and often unexpected ways. For instance, the strange and wonderful properties of materials at extremely low temperatures, like superconductivity and superfluidity, are quantum phenomena that can only be understood by taking into account the effects of zero-point energy. The jittery, restless behavior of particles is not confined to the world of matter alone. It extends to the very fabric of empty space itself, what we perceive as a vacuum, what we intuitively think of as a perfect, absolute emptiness, is, in reality, a dynamic and vibrant stage, teeming with a hidden quantum activity. The classical notion of a vacuum as a completely empty, inert, and passive space is replaced in quantum mechanics by the concept of the quantum vacuum, a seething, energetic field that is filled with the fleeting, ghostly presence of virtual particles. This quantum vacuum is a realm of constant and spontaneous fluctuation, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for the briefest of moments before annihilating each other and disappearing back into the void. These particles are called virtual because they do not exist as stable, long-lived entities, but their fleeting presence has real and measurable effects. One of the most stunning and famous examples of this is the Casimir effect. If you take two uncharged, perfectly parallel metal plates and place them incredibly close to each other in a perfect vacuum, you will find that there is a small but observable attractive force pushing them together. This force is not gravity. It is not electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain, specific wavelengths. While the space outside the plates can accommodate all possible wavelengths, this creates a pressure differential, a net force that pushes the plates towards each other. It is a beautiful, tangible, and direct demonstration that even the emptiest of spaces are rich with a hidden and powerful quantum activity. This concept of vacuum energy, the energy that is inherent in the quantum fluctuations of empty space, is further developed and explained by the powerful framework of quantum field theory. In the classical view, a field, like an electric or magnetic field, is a smooth and continuous entity that fills space. But quantum field theory, which is the result of combining quantum mechanics with special relativity, reveals that these fields themselves are inherently restless, discrete, and jittery. At every single point in space, at every moment in time, these quantum fields are fluctuating, vibrating, and seething with a latent potential energy. And the fundamental particles of our universe are not, in this picture, solid, independent entities. They are the excitations of these underlying fields, the localized, quantized disturbances or ripples within them. An electron is not a tiny, solid ball moving through space. It is a localized vibration in the electron field. A photon is a ripple in the electromagnetic field. The vacuum, in this framework, is simply the ground state of these fields, the state of their lowest possible energy. But this ground state is not a state of zero energy. It is a state of constant, irreducible, zero-point fluctuation. This vacuum energy is not confined to a single, isolated location. It is a universal property of space-time, a cosmic energy field that spreads throughout the entire universe, influencing the behavior of all particles and all forces, on both the smallest, microscopic scales and the largest, cosmological scales. Its effects are not just limited to the strange quantum realm of our laboratories. They ripple outwards, shaping the very structure and destiny of the universe itself. The ceaseless, restless energy of the vacuum is now believed to be the driving force behind the accelerated expansion of the universe, the mysterious phenomenon that we attribute to dark energy. The fate of the cosmos, its journey into an ever-expanding and perhaps eternal future, may be dictated by the subtle, yet powerful, quantum jitters of empty space. The role of the uncertainty principle in defining this jittery, probabilistic, and deeply interconnected reality cannot be overstated. It is the foundational principle, the master rule, from which so much of the strangeness and the beauty of the quantum world emerges. The principle does more than just set a limit on the precision with which we can measure certain properties of a system. It dictates the very nature of quantum existence. It is the reason that particles can exist in a superposition of multiple states at the same time. The reason that the act of measurement can collapse a world of possibilities into a single actuality. The reason that particles can be entangled across vast cosmic distances. These phenomena, which so deeply defy our classical intuition, are all direct consequences of the fundamental trade-off, the inherent complementarity, that is at the heart of the uncertainty principle. And it is this same principle that governs the ceaseless, energetic dance of the quantum vacuum. Because the quantum fields that make up our reality must obey the uncertainty principle. They can never, ever be perfectly still. Even in the complete absence of any real, stable particles, the vacuum is alive with the constant, spontaneous creation and annihilation of virtual particles, a process that creates a baseline level of energy out of what appears to be nothing at all. This energy, this zero-point energy, though often imperceptible in our everyday lives, has profound and far-reaching implications. It is the energetic foundation that underpins the stability of the very atoms that make up our bodies. In the classical, pre-quantum picture of the atom, an electron orbiting a nucleus should, according to the laws of electromagnetism, constantly radiate away its energy and spiral into the nucleus in a fraction of a second. The fact that atoms are stable, that matter exists at all, was a deep and profound mystery. The uncertainty principle provides the solution. If an electron were to fall into the nucleus, its position would be very precisely known. But this would mean that its momentum would have to be incredibly uncertain, meaning it would have a huge and unpredictable velocity that would instantly kick it out of the nucleus. The electron is trapped in a stable orbit not by a classical force, but by a quantum mechanical compromise, a dynamic equilibrium between the electrostatic attraction of the nucleus and the inherent uncertainty-driven jitter of its own, quantum nature. The restless, jittery activity of the quantum vacuum, this constant hum of creation and annihilation, is not just an abstract, theoretical concept. It manifests in a host of real, tangible, and experimentally verified ways. Consider the Lamb shift, a tiny but measurable difference in the energy levels of the hydrogen atom. In the simple early models of quantum mechanics, two particular energy levels in the hydrogen atom should have been exactly the same, but precise. Spectroscopic measurements in the 1940s showed that they were, in fact, slightly different. This tiny discrepancy was a major puzzle, and its explanation provided one of the first and most powerful confirmations of the reality of the quantum vacuum. The Lamb shift is caused by the interaction of the electron in the hydrogen atom with the virtual particles of the surrounding vacuum. The constant jittery fluctuations of the vacuum fields effectively smear out the position of the electron, slightly changing its interaction with the proton and shifting its energy levels. It is a direct, measurable consequence of the electron feeling the ceaseless, energetic dance of the void. Similarly, the quantum vacuum is crucial in explaining the phenomenon of spontaneous emission, the process by which an excited atom can spontaneously emit a photon of light and transition to a lower energy state. In the classical world, an excited atom would just stay excited forever unless it was perturbed by an external force. But in the quantum world, the zero-point fluctuations of the electromagnetic vacuum are always present, providing a constant, subtle perturbation that can stimulate the atom to decay and emit a photon. The stability of molecular bonds, the very foundation of chemistry and of life itself, is also deeply connected to the properties of the quantum vacuum. The forces that hold atoms together in a molecule are not just the simple electrostatic forces of classical physics. They are a complex quantum mechanical dance that is mediated by the exchange of virtual photons, a dance that takes place on the stage of the energetic, fluctuating vacuum. The concept of vacuum energy also raises profound and tantalizing questions about the very origins and the ultimate fate of our universe. Quantum field theory, in its current form, suggests that the energy density of the vacuum is not a fixed, static property, but is something that can evolve over time, influenced by the expansion of the universe and the dynamics of the underlying quantum fields. This perspective ties the smallest, most fundamental scales of quantum mechanics to the grandest, most cosmological questions we can ask. It bridges the gap between the micro and the macro, suggesting that the same jittery quantum restlessness that governs the behavior of a single atom is also the force that is driving the destiny of the entire cosmos. The jittery, fluctuating nature of the quantum fields also provides a new and more profound way to understand the deep, and often mysterious, interconnectedness of all things. In the classical worldview, the universe is a collection of separate, independent objects, interacting through local forces. But the quantum worldview, and particularly quantum field theory, paints a very different picture. At every single point in space, at every moment in time, all the quantum fields, the electron field, the photon field, the quark fields, the Higgs field are present, are active, are fluctuating, are interacting. There is no such thing as a truly isolated system. The behavior of a single particle is not just determined by its own intrinsic properties. It is influenced by the state of all the quantum fields that span the entire universe. The vacuum itself is a dynamic, ever-changing, and deeply interdependent entity. This perspective challenges our classical notions of separateness and locality, replacing them with a vision of reality as a single, holistic, and deeply entangled system. Through the lens of quantum mechanics, the universe appears not as a collection of things, but as a network of relationships, a seamless, interconnected tapestry of interwoven forces and energies. And the zero-point energy, the ceaseless, restless hum of the quantum vacuum, is the energetic thread from which this entire tapestry is woven. It is the source of all potential, the ground of all being, the silent, invisible, and endlessly creative engine of the cosmos. Quantum mechanics, in the end, does not provide us with all the answers. In fact, it often leaves us with more questions and deeper mysteries than we started with. But it does open the door to a new and more profound understanding of the universe's intricate, dynamic, and restless nature. It invites us to see the world not as a static, finished product, but as an ongoing, creative process. A universe that is constantly being born, moment by moment, from the beautiful, strange, and endlessly fascinating jitter of the quantum void. The quantum vacuum, this seething, energetic sea that underlies all of reality, is not just a theoretical curiosity. It exerts a real, tangible, and often profound influence on the physical world. The effects of the vacuum's incessant. Quantum fluctuations are not confined to the esoteric realm of high-energy physics. They are woven into the very fabric of our existence, from the stability of the atoms that make up our bodies to the grand, cosmological forces that shape the destiny of the universe. One of the most striking and direct demonstrations of the vacuum's power is its influence on the stability of matter itself. In the classical, pre-quantum picture of the atom, the orbiting electrons should, according to the laws of electromagnetism, constantly radiate away their energy and spiral into the nucleus in a fraction of a second. The fact that atoms are stable, that matter as we know it can exist at all, was a deep and profound mystery. The solution lies in the strange, jittery dance of the quantum world. The electrons in an atom are not tiny planets orbiting a central sun. They are probability waves, and they can only exist in specific, quantized energy levels. The lowest of these levels, the ground state, is not a state of zero energy or perfect stillness. It is a dynamic equilibrium, a state where the electron is constantly interacting with the zero-point fluctuations of the surrounding quantum vacuum. It is this incessant quantum jitter, this constant exchange of virtual photons with the vacuum, that prevents the electron from falling into the nucleus. The stability of the atom is not a static property. It is an active, dynamic process, a delicate balance between the electrostatic pull of the nucleus and the energetic push of the void. The vacuum is not just a passive stage. It is an active participant in the very constitution of matter. The influence of the quantum vacuum extends far beyond the scale of a single atom. It offers a new and deeper understanding of the fundamental forces that operate on the grand, cosmic scales of the universe. In the context of Einstein's general theory of relativity, the energy density of the vacuum contributes to the overall curvature of space-time, the very geometry that governs the motion of galaxies and the expansion of the cosmos. This provides a deep and beautiful connection between the microscopic world of quantum fluctuations and the macroscopic world of gravitational interactions. As we have seen, the leading hypothesis for the mysterious dark energy that is driving the accelerated expansion of our universe is that it is the macroscopic manifestation of the vacuum's own intrinsic zero-point energy. This is a breathtaking idea. It suggests that the same jittery quantum fields that are responsible for the subtle behavior of a single subatomic particle are also the primary engine shaping the long-term evolution and the ultimate fate of the entire universe. The implications are profound. It means that the destiny of the cosmos is not just being written by the visible matter and energy that we can see, but by the invisible, and far more abundant, energy of the emptiness itself. This insight bridges the gap between the very small and the incomprehensibly vast, offering a new and more unified vision of how the universe operates. But the influence of the vacuum is not just about expansion. Theoretical models suggest that the same quantum fluctuations that are driving the universe apart today may have played a crucial role in the very formation of its structure in the first place. During the period of cosmic inflation, the tiny microscopic fluctuations in the quantum fields of the early universe would have been stretched to astronomical scales, creating the seeds of density variation that would later, under the influence of gravity, grow into the vast cosmic web of galaxies and clusters that we see today. The grand, intricate architecture of the cosmos is, in this sense, a frozen, macroscopic snapshot of the primordial quantum jitter. The uncertainty principle, as we have seen, lies at the very heart of these quantum connections. It is the master rule that shapes the behavior of all quantum systems, from a single particle to the entire universe. It is not just a limit on what we can know. It is a fundamental statement about the nature of existence. By enforcing a minimum, irreducible level of activity, even in the complete absence of any real particles, the uncertainty principle ensures that the vacuum is never truly empty, that it is always a source of dynamic, creative energy. This has profound consequences. It is this dynamic nature of the vacuum that is reflected in phenomena like the spontaneous emission of light from an excited atom. In the classical world, an atom in an excited state would simply stay there forever unless it was perturbed by an external force. But in the quantum world, the constant zero-point fluctuations of the electromagnetic vacuum are always present, providing a subtle but ever-present kick that can stimulate the atom to decay and to release a photon. It is the jitter of the void that makes the universe a luminous and not a darkened place. The uncertainty principle also sheds new light on the origin of the universe's fundamental constants, the parameters that govern our reality, the strength of the fundamental forces. The masses of the elementary particles are not, in our current theories, fixed by any deep underlying principle. They are numbers that we must measure, but in a deeper, more complete theory. These constants may not be arbitrary. They may be emergent properties, determined by the complex, self-consistent interactions of all the quantum fields within the vacuum. The constants have the values they do because they are part of a stable, self-consistent quantum reality. A reality that is constantly being shaped and sustained by the restless, jittery dance of the void. This connection between the fundamental properties of nature and the dynamics of the quantum vacuum reveals a deep and beautiful interdependence, a picture where the smallest scales of reality influence the largest, and where the most fundamental constants of nature are not just static numbers, but are the dynamic result of the universe's own, ongoing quantum activity. While the vacuum is often described as empty, this description is a profound misnomer that masks its true and deeply complex nature. At the quantum level, what appears as emptiness is, in fact, a seething, vibrant arena of ceaseless possibility. Virtual particles, these ghostly, fleeting entities, are constantly emerging from the void and interacting with each other before vanishing back into the nothingness from which they came. This contributes to a constant background level of energy, a vacuum energy that, while incredibly subtle, has profound and far-reaching implications for our understanding of the universe's origin, its evolution, and its ultimate fate. The observed, accelerated expansion of the cosmos, the phenomenon we attribute to the mysterious dark energy, is the most dramatic and large-scale manifestation of this vacuum energy. If this connection holds, it would mean that the same jittery quantum vacuum that governs the behavior of the subatomic world is also the cosmic engine that is determining the long-term trajectory of the entire universe. Quantum field theory provides the mathematical framework that allows us to understand these strange and beautiful dynamics. It extends the principles of quantum mechanics from individual particles to the continuous, all-pervading fields that are the true, fundamental constituents of reality. In this picture, the classical notion of a smooth, continuous field is replaced by a quantum field that is inherently discrete, probabilistic, and fluctuating. These fluctuations are not random, chaotic noise, they are governed by the precise and elegant rules of quantum mechanics. And at every single point in space, at every moment in time, these fields are rippling with a latent, potential energy, creating particles not as independent, solid entities, but as localized, quantized disturbances within the field itself. This paradigm shift, from a universe of particles to a universe of fields, transforms our entire understanding of matter, of energy, and of the forces that govern them. It offers a single, coherent, and beautiful framework that can unite the seemingly separate realms of particles and fields into a single, unified reality. The quantum vacuum also plays a pivotal and often underappreciated role in the emergence of the fundamental forces of nature. The electromagnetic force, for example, which governs the interactions of charged particles, arises from the exchange of virtual photons, the quantum excitations of the electromagnetic field. These virtual photons are constantly bubbling up from the vacuum, mediating the force between charged particles and then disappearing back into the void. The same fundamental principle applies to the strong and the weak nuclear forces, which govern the behavior of atomic nuclei. The forces of nature are not static properties. They are dynamic, quantum processes, a constant, ongoing conversation between particles and the vacuum. Even gravity, which we traditionally view through the classical geometric lens of Einstein's general relativity, is now understood to interact with the quantum vacuum. The search for a theory of quantum gravity is, in many ways, a search for an understanding of how the jittery, fluctuating nature of the quantum world can be reconciled with the smooth, continuous curvature of space-time. One of the most striking and creative consequences of the vacuum's energy is its role in the phenomenon of spontaneous symmetry breaking in the incredibly hot and dense conditions of the early universe. It is thought that the four fundamental forces of nature were unified into a single, symmetric superforce. As the universe expanded and cooled, the quantum fields that mediate these forces underwent a series of phase transitions, similar to the way that water freezes into ice. In these transitions, the initial, perfect symmetry was broken, giving rise to the distinct and seemingly separate forces that we see in the universe today. The jittery, restless, and dynamic nature of the quantum vacuum, with its constant activity, is what drives these symmetry-breaking events. Without this process, the universe might have remained a featureless, symmetric, and ultimately lifeless expanse. It is the breaking of the perfect symmetry of the initial state that gives rise to the rich, complex, and beautifully diverse universe we inhabit. The uncertainty principle, as we have seen, is the ultimate source of this cosmic creativity by enforcing a fundamental and irreducible limit on what can be known and measured. It ensures that the quantum world remains a dynamic, probabilistic, and interconnected system. It is a principle that is not merely a restriction on our knowledge, but is a source of the very phenomena that make the quantum realm so strange and so wonderful. It is the reason for the dual, wave-particle nature of matter. It is the source of the probabilistic outcomes of our measurements. And it is the engine behind the ceaseless, energetic fluctuations of the quantum fields and the vacuum energy. Through this lens, the uncertainty principle emerges not as a barrier to our understanding, but as a gateway to a deeper, more profound appreciation of the intricate, dynamic, and endlessly restless nature of reality itself. It is the universe's way of ensuring that there will always be more to discover, more to wonder at, more to explore. And it is a reminder that the world we live in is not a static, finished product, but an ongoing, creative, and beautiful dance between the known and the unknown, between certainty and possibility, between the particle and the wave. The universe is vast, mysterious, and, in a way that is both beautiful and deeply puzzling, seems to be surprisingly well suited for the existence of life. This observation, the fact that the fundamental laws and constants of nature appear to be exquisitely fine-tuned to allow for the emergence of complex structures, of stars, of planets, and of conscious observers like ourselves, has led scientists and philosophers to explore a fascinating and controversial concept known as the anthropic principle. In its essence, the anthropic principle proposes that the reason we observe a universe with these specific, life-friendly properties is because, if the properties were any different, we would not be here to observe them. Imagine a universe where the force of gravity was just a little bit stronger. Stars would burn through their fuel much more quickly, and would likely collapse into black holes long before complex life could have a chance to evolve on any orbiting planets. If gravity were just a little bit weaker, matter would never have clumped together to form stars and galaxies in the first place. The universe would be a cold, diffuse, and lifeless soup of gas. The same delicate balance applies to a host of other physical constants. The strength of the nuclear force, the mass of the electron, the value of the cosmological constant, all of these seem to be sitting in a very narrow and very special range of values that allows for the existence of a universe that is both stable enough and complex enough to support life. The anthropic principle offers a potential explanation for this apparent cosmic coincidence. It shifts the focus from asking why the universe is so perfectly balanced to simply acknowledging that our own existence as observers is a powerful form of selection bias. We are, by definition, living in a universe that is capable of producing us. This idea has sparked a great deal of debate and reflection. Some see it as a profound insight into the nature of our relationship with the cosmos, a recognition that we are not separate from the universe we observe, but are an integral and significant part of it. Others view it as a mere tautology, a statement that is true by definition, but which lacks any real explanatory power. This debate is brought into sharp focus by the concept of a designer. The apparent purposeful design of the universe has long been used as an argument for the existence of a divine creator. But the anthropic principle offers a potential, naturalistic alternative. The argument for design without a designer, is perhaps best illustrated by the process of biological evolution. The intricate complexity and apparent design of a living organism, like the human eye, was once seen as irrefutable evidence for a divine watchmaker. But Charles Darwin's theory of evolution by natural selection showed how this complexity could arise gradually, through a long and completely natural process of random mutation and non-random selection. In the same way, the fine-tuning of the universe may not require a cosmic designer. Instead, it could be the result of a similar cosmic scale process of selection. The most popular and well-developed version of this idea is the multiverse. If our universe is just one of a vast, and possibly infinite, number of other universes, each with its own randomly assigned set of physical laws and constants, then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a life-friendly universe. It is a statistical inevitability. We are simply the lucky winners of a cosmic lottery of unimaginable proportions. This cosmic landscape, a term that comes from string theory, which predicts a vast number of possible vacuum states, each corresponding to a different set of physical laws, provides a concrete, physical mechanism for generating the ensemble of universes that the anthropic principle requires. The idea of a designer is appealing because it offers a simple and emotionally satisfying explanation for the complexity we see around us. But it is an explanation that ultimately leads to an infinite regress. If the universe was designed by a creator, then who or what designed the creator? The multiverse, on the other hand, offers a potential scientific explanation that is grounded in the known, or at least plausible, laws of physics, without the need to invoke a supernatural entity. The anthropic principle also forces us to confront the deep philosophical implications of our own existence. If life is a rare and special outcome of the universe's physical laws, a fortunate roll of the cosmic dice in a vast and mostly sterile multiverse, what does that say about our place in the cosmos? For some, this perspective can be a source of humility, a reminder of the incredible fragility and preciousness of our own conscious existence. It can foster a sense of responsibility, a recognition that we are the custodians of a rare and beautiful cosmic experiment. For others, however, it can feel diminishing. It can lead to a sense of cosmic loneliness, of our lives being devoid of any grand cosmic purpose, the universe. In this view does not care about us, it simply is. The meaning of our lives is not something that is given to us by the cosmos. It is something that we must create for ourselves, in the face of a vast and ultimately indifferent reality. This existentialist perspective is a powerful and challenging one, and it is a direct consequence of taking the implications of modern cosmology seriously. The anthropic principle also touches on the very nature of scientific inquiry itself. It is a principle that is not, in the traditional sense, falsifiable. We can never, even in principle, observe the other lifeless universes in the multiverse. This has led some to argue that the anthropic principle is not a true scientific explanation, but a philosophical one. But others argue that this is too narrow a view of science. A good scientific theory is not just one that makes testable predictions. It is also one that provides a deep, coherent, and satisfying explanation for the world we see. And the anthropic principle, when combined with the multiverse, does provide a potential and deeply compelling explanation for one of the most profound and otherwise inexplicable features of our universe, its hospitality to life. The debate over the anthropic principle is a debate that is likely to continue for a long time. It is a debate that is not just about the laws of physics, but about the nature of explanation, the limits of science, and the very meaning of our own human existence. And as we continue to probe the universe, to refine our theories, and to push the boundaries of our knowledge, we are not just learning more about the cosmos, we are also learning more about ourselves, about the remarkable, and perhaps even necessary, conditions that have allowed for the emergence of a conscious, questioning, and meaning-seeking being in the midst of a vast and beautifully fine-tuned cosmic mystery. For centuries, scientists have been on a quest to understand the universe, from its smallest particles to its largest structures. Thanks to remarkable advancements in technology and groundbreaking experiments, we are now able to peer into the farthest reaches of space and time, uncovering insights that were once beyond our wildest dreams. Some of the most intriguing, and also most perplexing, of these discoveries have come from the study of dark energy, of cosmic inflation, of the energy of the vacuum, and of the tantalizing, if speculative, possibility of a multiverse. These are concepts that are not just reshaping our understanding of the universe. They are providing evidence that challenges our most long-held assumptions and is inviting us to think about the cosmos in new and often counterintuitive ways. What if the universe is not as simple or as singular as we once thought? What if the things we cannot see, the forces we do not yet understand, play a much larger and more fundamental role in shaping reality than we ever imagined? These are the kinds of profound and exciting questions that are driving the frontiers of modern cosmology. One of the greatest of these frontiers is the mystery of dark energy. In the late 20th century, astronomers made a discovery that shook the very foundations of cosmology. By observing distant Type Ia supernovae, they found that the expansion of the universe is not slowing down. as had been expected due to the mutual gravitational pull of all the matter in the cosmos. Instead, the expansion is accelerating. This implied the existence of a mysterious, repulsive force, a form of dark energy that is pushing space-time apart. This dark energy is now thought to make up roughly 70% of the total energy density of the universe, making it the dominant component of our cosmos. But what is it? And how do we study something that we cannot directly see? The answer lies in studying its effects. The light from those distant supernovae, which act as standard candles with a known intrinsic brightness, allows us to measure the expansion history of the universe with incredible precision. And these measurements have consistently confirmed the presence of an accelerating expansion. Another powerful tool is the study of the cosmic microwave background, the faint afterglow of the Big Bang. The detailed patterns of temperature fluctuations in the CMB provide a snapshot of the universe when it was just a few 100,000 years old. And by analyzing these patterns, cosmologists can infer the total amount of dark energy in the universe and how it has influenced the growth of cosmic structure over time. These two independent lines of evidence from the late universe and the early universe both point to the same startling conclusion: our universe is dominated by a strange, invisible, and repulsive form of energy that is driving it towards an ever-accelerating future. The discovery of cosmic acceleration has given a new impetus to another, equally profound idea in cosmology: the theory of cosmic inflation, first proposed in the 1980s by the physicist Alan Guth. Inflation is the idea that the universe underwent a brief, but incredibly powerful, period of exponential expansion in the very first moments after the Big Bang. This rapid, hyper-accelerated growth would have stretched the fabric of space-time, smoothing out any initial irregularities and setting the stage for the large, flat, and uniform universe that we observe today. The theory of inflation is a beautiful and elegant one, and it solves a number of the deep conceptual puzzles of the standard Big Bang model. It also provides a natural mechanism for generating the initial density fluctuations that would later grow into the galaxies and large-scale structures we see today. But what is perhaps most fascinating about the theory of inflation is that it doesn't just explain the state of our current universe. It also provides insight into the very mechanisms that shaped its birth. The inflationary paradigm suggests that our universe may have been born from a tiny quantum fluctuation in a pre-existing high-energy vacuum state. It provides a framework for understanding why the universe is so vast, so old, and so structured in the way that it is. And the theory has been remarkably successful. Its predictions confirmed with stunning precision by our observations of the cosmic microwave background. As we continue to study the universe, we are constantly refining our understanding of this inflationary epoch. Some believe that inflation could have lasted for a much longer period than initially thought, or that it could have occurred in multiple distinct phases. And as we have seen, the idea of eternal inflation suggests that our universe may be just one of a vast and constantly growing number of pocket universes, each with its own unique properties. This brings us to the concept of vacuum energy, another key and deeply mysterious element of modern cosmological research. Vacuum energy is a form of energy that is thought to exist even in the perfect vacuum of empty space, where there is no matter or radiation. It arises from the constant quantum fluctuations that are an inherent feature of the quantum world. These fluctuations, where virtual particles pop in and out of existence, give rise to a baseline level of energy that fills all of space. And while this vacuum energy might sound like a subtle, abstract concept, its effects are anything but. In fact, many physicists believe that the vacuum energy of space is the physical reality behind the mysterious dark energy that is driving the accelerated expansion of the universe. As the universe expands, the amount of vacuum energy increases, contributing to the repulsive force that is pushing galaxies further and further apart. The connection between vacuum energy and dark energy is still a subject of intense research and debate. But it is clear that understanding the nature of the vacuum is crucial for understanding the fundamental forces that are at play in our cosmos. Looking towards the future, one of the most exciting and also most challenging areas of cosmological research involves the development of new telescopes and experiments that are designed to probe the very limits of our understanding, and perhaps even to test the speculative but deeply compelling hypothesis of the multiverse. The multiverse, as we have seen, is the theoretical concept that our universe may be just one of many, each with its own set of physical laws and constants. While the idea of a multiverse is still highly speculative and may forever lie beyond the realm of direct experimental verification, advances in technology and cosmology are bringing us closer to a point where we might be able to search for indirect circumstantial evidence. Future telescopes, like the now operational James Webb Space Telescope, are providing us with more detailed and more precise observations of distant galaxies, of exoplanets, and of the early universe than ever before. This data is allowing us to test our cosmological models with unprecedented accuracy, and to search for any subtle anomalies that might hint at new, undiscovered physics. If the multiverse hypothesis has any basis in reality, it is possible that we might one day detect the faint telltale signs of other universes, perhaps in the form of specific, non-random patterns in the cosmic microwave background, or in the discovery of anomalies in the fundamental constants of nature that could suggest the influence of other parallel realities. While this is still a long way from becoming a reality, the very potential for such a discovery is what drives the scientific quest forward. As our experiments and our telescopes continue to evolve, we may soon be able to answer some of the most profound and long-standing questions about the nature of the universe and our place within it. The field of cosmology is in a state of rapid and exciting evolution. The discovery of dark energy has shown us that our universe is a far stranger and more mysterious place than we ever imagined. The theory of cosmic inflation has provided us with a powerful and elegant framework for understanding its origins. And the ongoing study of vacuum energy is offering new and often puzzling clues into the fundamental forces that are shaping its destiny. As we continue to push the boundaries of our knowledge, one thing is clear: the universe is far more complex, more beautiful, and more wonderfully mysterious than we ever dreamed. And the discoveries we make in the coming years will continue to challenge, to inspire, and to expand our understanding of the grand cosmic story in which we all play a small but not insignificant part. The debate surrounding the anthropic principle and its connection to the concept of a multiverse stands as one of the most contentious and also most thought-provoking issues in contemporary physics and cosmology. At its heart, it is a debate about the very nature of scientific explanation and about the limits of what we can ever hope to know about the universe. On the one hand, we have the startling and seemingly undeniable fact of our own existence. We live in a universe that appears to be exquisitely and improbably fine-tuned to allow for the emergence of complexity, of life, and of conscious observers. The fundamental constants of nature, the strength of gravity, the charge of the electron, the value of the cosmological constant all seem to be sitting in a very narrow and very special range of values. A slight tweak in any one of them, and the universe as we know it would not exist. The anthropic principle, in its weak form, simply acknowledges this as a form of selection bias. Of course, we find ourselves in a life-friendly universe. We could not have found ourselves anywhere else. This is illogical, but not particularly deep. Explanation: the strong version of the principle, which suggests that the universe must have properties that allow for life. veers into the realm of metaphysics and teleology. But the weak anthropic principle finds a powerful and scientifically respectable partner in the theory of the multiverse. If there are a vast, and perhaps infinite, number of other universes, each with its own, randomly assigned set of physical laws and constants, then the fine-tuning of our own universe is no longer a miracle. It is a statistical inevitability. We are simply living in one of the rare, habitable oases in a vast and mostly sterile cosmic desert. This is a powerful, and for many, a deeply satisfying explanation. But it is an explanation that comes with a heavy philosophical price. It requires us to accept the existence of a potentially infinite number of unobservable realities, a concept that many find to be a violation of the principle of scientific parsimony. This tension between the empirical and the theoretical, between what we can observe and what we can infer, highlights an ongoing and often passionate philosophical debate about the very boundaries of science itself. Critics of the multiverse and the anthropic principle argue that they are not true scientific theories. A scientific theory, in the traditional Popperian view, must be falsifiable. It must make risky, testable predictions that, if they are not borne out by experiment, would force us to abandon the theory. But the multiverse, by its very definition, seems to be unfalsifiable. We can never travel to another bubble universe to check if its physical laws are different. And so, for the critics, the multiverse is not science. It is a form of recreational mathematics, a philosophical or metaphysical speculation that is dressed up in the language of physics. Supporters of the multiverse, on the other hand, argue that this is too narrow and too rigid a view of what constitutes science. They point out that the theories from which the multiverse arises, like cosmic inflation and string theory, are themselves, in principle, testable. Inflation, for example, makes specific predictions about the statistical properties of the cosmic microwave background, predictions that have been stunningly confirmed. And while string theory has not yet made a unique, testable prediction, it is a rich and ongoing research program that could one day do so. The multiverse, in this view, is a logical, and perhaps even unavoidable, consequence of our best and most successful physical theories. To reject the multiverse simply because it is not directly observable would be to reject the very theories that have been so successful in explaining the universe we can see. This debate highlights a deep and often unspoken tension within the scientific community itself. There is a constant interplay between the drive for empirical verification and the pull of theoretical elegance and explanatory power. When scientists explore the fine-tuning of the universe, they are not just doing physics, they are engaging with questions that have traditionally been the domain of metaphysics, of philosophy, of theology. They are asking questions about existence, about necessity, about the ultimate causes of reality. Does this integration enrich scientific inquiry, or does it dilute its empirical rigor? Can metaphysical perspectives offer meaningful insights into the deep questions of cosmology, or do they risk overstepping into a realm of untestable and ultimately unscientific? Speculation. There is no easy answer to these questions. They point to the complex and often blurry boundary between science and philosophy, a boundary that is constantly being negotiated and redrawn as our knowledge evolves. The study of the fine-tuning of the universe and the possibility of a multiverse also brings a host of ethical considerations into sharp focus. The pursuit of these ideas requires a vast investment of public resources, the construction of massive particle accelerators, the launching of sophisticated space telescopes, the funding of generations of theoretical physicists. This raises important questions about scientific priorities. In a world with so many pressing, practical challenges, from climate change and disease to poverty and conflict, Is it ethically justifiable to spend billions of dollars on the pursuit of knowledge that may be purely abstract and may never have any direct, practical application? Critics would argue that these resources could be better spent on research that has a more immediate and tangible benefit to humanity. Proponents, on the other hand, would argue that the pursuit of fundamental knowledge is one of the highest and most noble of all human endeavors. It is an expression of our deepest curiosity, our desire to understand our place in the cosmos. And history has shown, again and again, that breakthroughs in fundamental science, even those that seem purely abstract at the time, often lead to unexpected and revolutionary practical applications. The development of quantum mechanics, for example, was driven by a pure, intellectual curiosity about the nature of the atom. But it has led directly to the technologies of the digital age, from the transistor and the laser to the MRI machine and the GPS. The ethical implications of these debates also extend to the very content of the theories themselves. The idea that our universe is just one of a vast and mostly sterile multiverse, and that our own existence is a mere statistical accident, can be a deeply unsettling one. It can challenge long-held religious and philosophical beliefs about the specialness of humanity, about the existence of a cosmic purpose, about the very meaning of our lives. Scientists have a responsibility to communicate these ideas with care, with nuance, and with a deep sensitivity to their potential, cultural and psychological impact. They must be clear about what is established, scientific fact, and what is speculative, theoretical possibility. The dialogue between science and the broader culture is a crucial one, and it is one that requires a sense of mutual respect and intellectual honesty from all sides. The ongoing debate over the anthropic principle, the multiverse, and the fine-tuning of the cosmos is a vibrant and healthy one. It is a sign of a science that is grappling with its own deepest and most profound questions. It is pushing the very boundaries of what we consider to be empirical inquiry, and it is forcing us to engage in a new and more sophisticated dialogue between physics, philosophy, and ethics. The disagreement between those who see the universe as a unique, and perhaps necessary, creation, and those who see it as a random and fortunate accident is a reflection of a deep and enduring tension in human thought. It is the tension between the search for a single, unifying explanation and the acceptance of a vast and perhaps incomprehensible diversity as we continue to explore the universe, to refine our theories, and to push the limits of our observational capabilities. We may one day find evidence that will tip the scales in one direction or the other. Or we may find that the answer is something far stranger and far more beautiful than we can currently imagine. But whatever the outcome, the very process of engaging with these questions, of daring to ask about the ultimate nature of reality, is a process that enriches our understanding, deepens our sense of wonder, and ultimately elevates the human spirit. The cosmological constant is one of the most enigmatic and also most powerful concepts in all of modern physics. It is a single number, a simple term in Einstein's equations of general relativity, but it is a number that seems to hold the key to the ultimate destiny of our universe. The story of the cosmological constant is a dramatic one, a tale of rejection, of redemption, and of deep and still unresolved mystery. Albert Einstein first introduced the cosmological constant into his theory in 1917. At the time, the prevailing view was that the universe was static, eternal, and unchanging. But Einstein's own equations of general relativity seemed to predict a dynamic universe, one that should either be expanding or contracting under the influence of gravity. To reconcile his theory with the prevailing cosmological wisdom, Einstein added a new term to his equations, a fudge factor that represented a kind of cosmic anti-gravity, a repulsive force inherent in the fabric of space-time itself that would perfectly balance the attractive force of gravity and allow for a static universe. But this static universe turned out to be unstable, and more importantly, it turned out to be wrong. In the 1920s, the American astronomer Edwin Hubble, through his meticulous observations of distant galaxies, made the revolutionary discovery that the universe is not static. It is expanding. The galaxies are all moving away from each other, and the further away they are, the faster they are receding. Upon hearing of Hubble's discovery, Einstein is said to have abandoned his cosmological constant, calling it his biggest blunder. For decades, the cosmological constant was relegated to the dustbin of scientific history, a curious footnote in the story of general relativity. But in a stunning and beautiful twist of fate, the blunder was resurrected in the late 20th century by studying distant Type Ia supernova. Astronomers found that the expansion of the universe is not just continuing, it is accelerating. This implied the existence of a mysterious, repulsive force, a dark energy that is pushing the cosmos apart, and the simplest and most natural mathematical representation for this dark energy is Einstein's old and once reviled cosmological constant. The cosmological constant, in its modern interpretation, is thought to be the physical manifestation of the vacuum energy, the zero-point energy of the quantum fields that permeate all of space. As we have seen, the quantum vacuum is not an empty nothingness, but a seething, energetic sea of virtual particles. And this energy, according to general relativity, has a gravitational effect. A constant vacuum energy density would exert a strong, negative pressure, a repulsive force that would drive the accelerated expansion of the universe. This is a beautifully elegant and unifying idea. It connects the strange, microscopic world of quantum fluctuations with the grand, macroscopic dynamics of the cosmos. But it also leads to one of the most profound and embarrassing problems in all of theoretical physics, the vacuum catastrophe. When physicists try to calculate the expected value of the vacuum energy based on the principles of quantum field theory, they get a number that is astronomically, absurdly large. It is about 120 orders of magnitude, a 1, followed by 120 zeros larger than the observed value of the cosmological constant that is needed to explain the cosmic acceleration. This is so as without a doubt the single worst theoretical prediction in the entire history of science. It is a sign that there is something deep and fundamentally wrong with our current understanding of the relationship between quantum mechanics and gravity. Why is the observed energy of the vacuum so incredibly, exquisitely small compared to the theoretical prediction? This is the cosmological constant problem, and it is a puzzle that has haunted physicists for decades. If the vacuum energy were as large as the theory suggests, the universe would have been torn apart in the first fraction of a second of its existence. The fact that we live in a universe that is both long-lived and capable of forming complex structures like galaxies and stars means that there must be some unknown and incredibly precise mechanism that is canceling out almost all of the vacuum energy, leaving just the tiny residual amount that we observe as dark energy. The fine-tuning of the cosmological constant is so extreme that it has led many physicists to embrace the anthropic principle and the idea of a multiverse. If there are a vast number of other universes, each with its own randomly determined value for the cosmological constant, then it is no surprise that we find ourselves in one of the rare universes where this value is small enough to allow for our own existence. In this cosmic landscape of possibilities, we are the winners of an almost impossibly unlikely cosmic lottery. But this is an explanation that many find to be deeply unsatisfying. It is a retreat from the traditional goal of physics, which is to find a unique and necessary explanation for the properties of our universe. The cosmological constant problem also highlights the deep, and as yet unresolved, connections between the quantum world and the world of general relativity. The cosmological constant is the point where these two great theories meet, and it is the point where they seem to be in most violent conflict. The resolution of this problem will almost certainly require a full, and as yet undiscovered, theory of quantum gravity, a theory that can consistently describe the quantum nature of space-time itself. But the cosmological constant is not just a theoretical puzzle. It is a key determinant of the ultimate fate of our universe. If the dark energy it represents is truly constant, then the universe will continue to expand at an accelerating rate forever. The galaxies will recede from each other, the sky will grow dark, and the universe will end in a cold, lonely, big freeze. If, on the other hand, the dark energy is not a constant, but a dynamic field that could change its value over time, then other, more dramatic, fates are possible, including a big rip where the very fabric of space-time is torn apart. The cosmological constant is a single, simple number, but it is a number that contains within it some of the deepest and most profound mysteries of the cosmos. It is a window into the strange, energetic nature of the void. It is a key to understanding the past, the present, and the ultimate future of our universe. And it is a stark and humbling reminder of the vast, uncharted territory that still lies at the very frontier of our scientific understanding. The future of our quest to understand the universe is a story of ever-advancing technology, of ever-deepening theoretical insight, and of an unquenchable and uniquely human curiosity. We are living in a golden age of cosmology, a time when new discoveries are being made at an unprecedented rate, and when we are poised to answer some of the longest-standing and most profound questions about our cosmic origins. The next generation of telescopes and experiments, both on the ground and in space, will push the boundaries of our knowledge into new and previously inaccessible realms. The James Webb Space Telescope is already giving us our first stunning glimpses of the cosmic dawn, the era when the very first stars and galaxies lit up the universe. In the coming years, it will continue to map this ancient frontier, to study the formation and evolution of the first cosmic structures, and to search for the chemical fingerprints of life in the atmospheres of distant exoplanets. On the ground, massive. New 30-meter class optical telescopes will provide a powerful synergy with Webb, allowing for detailed, high-resolution follow-up studies of the most interesting objects it discovers. The search for the nature of dark matter and dark energy, the two great invisible components of our universe, will enter a new era of precision. The Vera C. Rubin Observatory in Chile will conduct a decade-long legacy survey of space and time, creating a deep, multicolor movie of the southern sky. Its vast trove of data will allow cosmologists to map the distribution of dark matter through weak gravitational lensing on an unprecedented scale, and to trace the history of cosmic expansion with thousands of new supernovae, providing the most stringent tests yet of the nature of dark energy. The European Space Agency's Euclid mission will provide a complementary, high-resolution view from space, mapping the shapes and redshifts of billions of galaxies to create a three-dimensional map of the cosmic web. And deep underground, in heavily shielded laboratories, a new generation of highly sensitive detectors will continue the direct search for the elusive dark matter particle, hoping to catch the faint, rare signal of a dark matter particle interacting with an atom of ordinary matter. But perhaps the most exciting new frontier in cosmology is the dawn of gravitational wave astronomy. Since the first historic detection of gravitational waves in 2015 by the LIGO Observatory, we have opened a completely new window onto the universe, a window that allows us to hear the cosmos, not just see it, The current network of ground-based detectors is constantly being upgraded, increasing its sensitivity and allowing us to detect the faint ripples in space-time from the mergers of black holes and neutron stars at ever greater distances. But the ultimate goal is to take gravitational wave astronomy into space. The Laser Interferometer Space Antenna, a planned mission for the 2030s, will consist of 3 spacecraft flying in a triangular formation, separated by millions of kilometers. LISA will be a gravitational wave observatory of truly cosmic proportions, sensitive to the low-frequency gravitational waves that are inaccessible from the ground. It will be able to detect the mergers of supermassive black holes at the centers of distant galaxies, providing a new way to study the coevolution of galaxies and their central black holes. And most excitingly of all, LISA may be sensitive enough to detect the faint, stochastic background of primordial gravitational waves that are predicted to have been generated during the period of cosmic inflation in the first fraction of a second after the Big Bang. The detection of these primordial gravitational waves would be a monumental discovery, a smoking gun confirmation of inflation, and a direct glimpse into the physics of the universe at energies that are 1 trillion times higher than anything we can achieve in our terrestrial particle accelerators. It would be a window into the very moment of creation. Alongside these remarkable observational advances, the theoretical quest will continue. The search for a unified theory of quantum gravity, the holy grail of modern physics, will be guided and constrained by these new, precise data. Advances in string theory, in loop quantum gravity, and in other, more speculative, approaches may lead to a breakthrough in our understanding of the fundamental nature of space, of time, and of reality itself. And the rapidly developing field of quantum computing may one day provide us with a new and incredibly powerful tool for simulating the complex quantum dynamics of the early universe, allowing us to test our theories in a new virtual laboratory. Despite all these remarkable and ever-advancing tools and theories, it is possible, and perhaps even likely, that some of the deepest questions about the origin and nature of the universe will forever remain beyond our grasp. There are fundamental, built-in limits to what we can know. The cosmic horizon limits how far we can see. The Planck scale may represent a fundamental limit to the resolution with which we can probe the fabric of reality. And the multiverse, if it exists, may be forever beyond the reach of direct experimental verification. These limitations are not a sign of failure. They are a reminder of our own human finitude, a call to a sense of intellectual humility. They bring us back to the great, timeless philosophical questions that have animated the human spirit since its inception. Why is there something rather than nothing? Does the universe have a purpose? What is the nature of consciousness? And what is our place in the grand cosmic scheme of things? Science can illuminate many aspects of these questions. It can push back the boundaries of our ignorance. It can reveal the deep and beautiful order of the natural world. It can provide us with a powerful and coherent story of our cosmic origins. But it may not be able to provide the final, ultimate answers. Some dimensions of these questions may always remain in the realm of philosophy, of art, of religion, of personal, subjective experience. And this is not a weakness. It is a strength. It is a recognition of the richness and the complexity of the human quest for meaning, a quest that is not reducible to a single scientific framework. We end, then, where we began, with a sense of profound and beautiful awe at a universe that is both deeply comprehensible and endlessly mysterious. With each new discovery, the island of our knowledge grows, but so does the shoreline of our ignorance. As you lie in the quiet of the night, on the peaceful threshold of sleep, you can feel a sense of participation in this grand human adventure. The very consciousness that is listening to these words, that is contemplating the origin of the cosmos, is a part of that cosmos, a part of the universe that has, through a long and improbable evolutionary journey, woken up and begun to ask questions about itself. The atoms in your body were forged in the hearts of long-vanished stars. The energy that powers your thoughts is part of the same cosmic flow that drives the galaxies, and your consciousness, whatever its ultimate nature may be, is one of the most remarkable and most beautiful phenomena in a universe that was born from a seeming nothingness to come to know itself. Good night, and may your dreams be as vast, as mysterious, and as wonderful as the cosmos that is your home.